All right, this is page 211, question number 13. It describes a horizontal spring mounted on the end of a lab bench to shoot marbles at targets on the floor. I'm going to hope that you can find that question yourself and in the textbook. Page 211, number 13. Okay, so it describes this horizontal spring mounted on the end of a lab bench. So here's like a desk or a lab bench or whatever. The desk gets described as 93 centimeters high. This horizontal spring is mounted here. It's going to be compressed back. I think it mentions compressed back by 4 centimeters. So it's compressed backwards by 4 centimeters. A ball is placed next to it. We're going to kind of take that as position 1. When we let this thing go, the spring is going to uncompress. It's going to push the ball towards the end of the lab bench. By the time it's here, the spring, we're going to assume, is completely uncompressed. The ball then leaves the spring and the lab bench, becomes a projectile, flies through the air and lands here. We're going to consider 3 positions. The first position is when the spring is compressed. The second position is when the spring is uncompressed, but the little ball, whatever this thing is the marble, I guess, is the spring is uncompressed, the marble's still on the bench, and then the marble's going to fly through the air and land on the ground over here. And our question is, what is dx? How far does the marble fly through the air? What does it say? Before hitting the floor. So it's going to hit the floor here. We're going to consider kind of step A, let's call it, I guess. Step A is going from position 1 to position 2. And then in a minute, so we'll do some stuff there. We're going to figure out, my goal here is to figure out how fast is it going here. Then from 2 to 3, it's going to become a projectile. And maybe over here we'll do from position 2 to 3, and we'll do some projectile motion to figure out how far it's gone. The question with this question often comes up, couldn't we just do conservation of energy straight from 1 to 3? And the answer is yes, we can. We can do conservation of energy straight from here to here. If they ask me like what was the final speed, no problem, we could do it. Because they want to know dx, there's no dx in conservation of energy, at least not unless you're talking about maybe friction or something, but there's no convenient dx to solve for this. So yes, we could do conservation of energy from here to here, or at least energy is conserved from 1 to 3. It's just not going to be helpful for us to do that. Okay, so from 1 to 2, let's write out the whole big equation. Most of this stuff is going to cancel out, but I'm just going to write it all out just to kind of keep in mind I'm considering everything for energy, everything that we know of anyways for energy. And when we consider this big long equation, I've kind of pre-written stuff here, but what I want to do is at position 1, I want to consider all those variables. What's V1, what's H1, what's X1, what's applied force? So if I look up here, we're told that this spring is compressed by 4 centimeters. Its initial velocity is 0. Its initial height, you could say it's 93 centimeters, but it's also going to be 93 centimeters here. So I'm going to consider that as height equals 0, which means it's still going to be 0 here. The applied force is 0. There's no applied force. Friction, there's no friction mentioned as it goes across here. It's a marble, I guess it's rolling or something. In real life, there's always friction, but good physics questions, we can ignore friction. What we're looking for then is V2. X2, as I mentioned, is going to be 0. So the spring is compressed here. By the time it gets here, the spring is fully uncompressed, and then the marble is going to fly through the air. Okay, so we know, well, I guess we can, let's do a little crossing out. That's always exciting. Cross that guy out. V1 is 0. H1 is 0. X is not 0. Applied force is 0. Over here, V2, I'm not sure what that is, but H2, 0. The spring is fully uncompressed. X is 0. Friction is 0. They don't mention it. What this kind of comes down to then is half K X1 squared is equal to half V2 squared. We can actually cancel those halves out, but what we're saying here is the elastic potential energy here all becomes kinetic energy by the time it's here. Now we can just sub some numbers in. We know K is 12. X1 is 4 centimeters. I'm going to convert that to meters. I just like everything in base units, and I don't need to think of as to what units I'm in. The mass, they listed in scientific notation. I'm going to convert it to not scientific notation. We can rearrange this, solve for V2, and we get something like this. Okay, this is not our answer, but this speed is how fast the marble is going right here as it leaves the spring. Now it becomes projectile motion. So I think I can fit stuff down here. Let's say step B. This is from position 2 to 3. This is this projectile motion part as it flies through the air. Thinking back to projectile motion, it's probably been a while, but I'm going to do it kind of the old-fashioned way, because that's the only way. What we know is this speed right here is how fast it is going horizontally, right as it's going to leave the lab bench. As always, horizontally, there's no acceleration. dx, that's what we're looking for. Time, we don't know time, but hopefully we can find it in the y direction. In the y direction, v1y is 0. This thing is going across the lab bench. When it's going this speed right here, okay, that speed, that is horizontally. It's still going in the horizontal direction. There's no y component, not yet. There will be some acceleration. So acceleration, I'll say negative 9.8 just to indicate that it's down. And let's say right here, up is positive, to the right is positive. Okay, so I'll say negative 9.8 just to say that it's down. dy, this table we're told is 93 centimeters. So let's actually convert that right into meters. And again, negative, just to indicate that our displacement, we're starting up high, we're ending down low. So this thing is going down. And I'm going to look for time. Once I find time, I can use it over here, solve for dx. So I'm kind of out of room over here, so let's sneak it over here a little bit. Let's say in the y direction, okay, so I'm using this y information. I know distance is v1t plus half at squared. We know our displacement right here. v1y is 0, okay, so that whole thing goes away. 1/2 acceleration times squared. Rearrange, solve for time. Let's see, 0.43566. That time then is also the time over here. Okay, so now when I go, let's do it over here, when I go into the x direction, really the equation that I'm using is this guy, same equation, the best friend equation. But remember, there's no acceleration. Remember this thing right here, ax is 0. That whole part goes away. So this dx that I'm looking for, that dx right there, is this speed times the time, which is this time, and that works out to 0.6626. So it's approximately 0.66 meters or 66 centimeters. And that's it.